Hello, everybody. Welcome back to Markov Chains. Okay, so we are getting into continuous time, but discrete state space Markov chains. Okay, so we're talking about continuous time Markov chains. I did say at the beginning that the word process is usually used for continuous time, but chains is fine as well. And it also makes for a more common acronym, which is CTMC, which again stands for continuous time Markov chains. Now, your assumption was always supposed to be that everything is discrete until it's not. And so I would keep that assumption about things that are not mentioned here, and that is the state space. So I would say continuous time and continuous state space. That's something we haven't gotten to yet, but I do mean a discrete state space. Or I would say continuous time, continuous space. Right, so this is like you're counting, I don't know, people, I keep doing the store thing, inter-arrivals to a store, and they're not coming at special discrete times, but it's a discrete number of people coming in each time. Okay, so last time I was doing some review of important distributions, and I have more of that to do, but I am going to break it up so that we're not just going to have another day of doing nothing Markov. So last time we talked about the exponential distribution, and the fact that I use this notation, exponential with rate lambda, not just lambda. And that's because I mean that the PDF is lambda e to the minus lambda x for x greater than 0, even x greater than or equal to 0, and 0 otherwise. And I'm a big fan of writing that in one line with indicators, but it's not really important like it is in a course in, say, mathematical statistics, where you're doing lots of manipulations with PDFs. My bracket does not reach. Okay, so some people write their exponential PDFs with a 1 over lambda every place I have a lambda. And that would mean that that is the mean of their distribution, because in our case, the mean of this random variable, the expected value of x, which is the integral of x times its PDF integrated over the whole space, will give you 1 over lambda. So if people come into your store at a rate of 4 per hour, then the expected amount of time between the arrivals, because this is always used to model an inter-arrival or inter-event or inter-occurrence time. So if they come in at a rate of 4 per hour, the inter-arrival time is expected on average to be 1/4 of the hour. So there's the relationship between the mean, 1 over lambda, and the rate, lambda. Okay, so the CDF, the cumulative distribution function, capital F of x, is the probability, as it's always been in all your probability courses. It's the cumulative probability that the random variable x is less than or equal to this argument little x. And you would get that by integrating the PDF up to x. I'm going to use a different letter just because I have an x in my limits of integration, although you can do it. And yeah, our PDF happens to start at 0. So we're only going to go from 0 up to x, lambda e to the minus lambda x dx. And if you do this, you'll get 1 minus e to the minus lambda x. And this is a CDF that we're going to use so often that, I mean, you don't have to memorize it, but you eventually will. You will realize you have it. Most distributions, we know a lot of PDFs. We don't know a lot of CDFs, but this one we're going to use so much that I'm hoping you'll get comfortable enough to just know the CDF automatically without any integration. Okay, so we're going to want to talk about a tail probability, which is the probability that our random variable x is actually above some number little x. And in the well, in either case, this is 1 minus the probability that x is less than or equal to x. And so this is 1 minus f of x, the capital F, the CDF. And we're going to use a lot of tail probabilities. So we're going to give this a name. I'm going to define, or a symbol, I'm going to define f bar of x to be 1 minus capital F of x. So this tail probability, the probability out in the tail of the distribution. And that is a really common notation.
Do you
That's why.
mean to have that bar over that second f of x?
No, thank you. Yeah, yeah. So there should not have been a bar up here because I'm defining f bar to be 1 minus the original f. Okay, so thank you for that. Last time we were talking about the lack of memory or memoryless property of the exponential. Lack of memory property of the exponential, which is going to be really crucial in kind of Markov calculations. My Tegu is lost in the mail, by the way. Yeah. Hopefully he's doing all right. Okay, so the lack of memory property says this, and this is for any random variable, although I will show you, prove to you that this actually will imply that the distribution must be exponential. But first we'll state it without assuming an exponential distribution. So I'm going to let like little s and little t be greater than or equal to 0. The lack of memory property says that if you have a random variable x, the probability that x is greater than s plus t is, conditional on that it's being already greater than s, is the probability that x is greater than t. So we'll prove this in a second, and it's really not hard at all. But I want to talk about the idea. So if you think of x as a time, we'll probably denote it by a capital T, but as a waiting time. And this is saying I've already waited s units of time and it hasn't happened yet. My waiting time is more than s. What's the probability I'm going to have to wait even more than t more? It's just the probability you have to wait more than t from the start. And so why this is so useful to us is if we have some kind of Markov process that changes at exponential times. Now, I haven't defined what it means to be a Markov process in continuous time, but it's going to be basically the same thing at any point in time. If you just decide to look at this, where you go should depend only on where you are and not where you've been. And yet, if we didn't have this lack of memory property, and I look at the chain at this particular time, I don't know exactly when I'm going to jump up next. I don't know the distribution of this leftover amount of time after this amount of time has already gone by. But the lack of memory property will say if the inter-arrival times are independent, exponential, then interrupting, so the horizontal line, the vertical line I drew is interrupting the process. And let me get color. The amount of time left to wait, this yellow, is still exponential if there was an exponential amount of time between all of the events. So let's prove the lack of memory property of the exponential. So x is going to be exponential with rate lambda. And I'm going to look at the left-hand side of what I wrote as the lack of memory property. And then this conditional probability, we can write out as the intersecting probability in the numerator and the second probability in the denominator. And then S and T are non-negative. So, what is the probability you're greater than 5 and also greater than 3? This is just kind of redundant. It's the probability you're greater than 5. So going back up to the proof, this is the probability that x is greater than s plus t over the probability that x is greater than s. And now we're seeing a couple of those tail probabilities. And because we maybe aren't used to it yet, you certainly don't have to do this. I just defined tail probabilities, but you can turn these around and use CDFs. And the CDFs already had 1 minuses in them. So if you go back and look at the CDF for the exponential, you get 1 minus e to the minus lambda s plus t over 1 minus e to the minus lambda s. And you get lots of cancellation. You get e to the minus lambda s plus t over e to the minus lambda s. And you get e to the minus t, lambda t, which is the tail probability for that exponential. This is 1 minus the CDF. So we can see that that lack of memory property holds when the random variable is exponential. Any questions on that? So now I want to tell you the extra special property of the exponential, and that this is actually an if and only if, at least for continuous random variables. So I want to prove to you that if you have a random variable with this lack of memory property, it must have the exponential distribution if it's a continuous random variable. There is an analog for discrete random variables, and that is the geometric distribution has this kind of lack of memory property if you're looking at discrete random variables. So I want to convince you that this is an if and only if. So I claim if x is a continuous random variable with I'm going to start writing this down because we're going to write this a lot. LOM, lack of memory, or memoryless, but that doesn't make for a good acronym. M. If it's a continuous random variable with a lack of memory property, it must be exponential, meaning it must have an exponential distribution, exponential, which I think is a very cool thing. So let's mostly prove this, although at one point I'm going to have to make a real analysis claim that I'm not sure all of you know, but it's not a big one. So the lack of memory, I defined it in terms of a conditional probability. But if we write out that conditional probability as the ratio that it is and move part of it to the other side, lack of memory is saying that the probability that our random variable x is greater than s plus t is the product of the probability that we're greater than s and the probability that we're greater than t. One of these was, this one was under this when it was written as a conditional probability. Just didn't want to take the time to rewrite that and then simplify it. And this is for any s and t greater than 0, real numbers. So in our new notation for tail probabilities, I'm going to use the f with the bar over it. And the first thing the thing on the left side of my equation is f bar s plus t. And on the right, I have f bar s and f bar t. Okay, so I'm assuming this holds. So this holds, and I'm trying to show it's an exponential random variable. So here's a bullet. I like using bullets and proofs, lists of things. Note that if you take s to be t, right? Then what you're seeing here is that f bar of 2t is f bar of t squared. And so from this, you can see as well that f bar of 3t, this is f bar of t plus 2t. So from the lack of memory property, this is f bar of t times, looks like a lambda or something, 2t. From the lack of memory property, this is f bar of t times f bar of 2t, but we just saw that f bar of 2t is f bar squared of t, so this is f bar cubed of t. And in general, f bar of nt is equal to f bar to the n of t for integers 1, 2, 3. Okay, so I started looking at f bar of 2t, f bar of 3t, etc. Now I want to kind of flip these over and talk about fractional values of t. So for my next trick or bullet, since f bar of 2t is equal to f bar squared of t, then this implies that f bar of t is equal, so this held for any real t greater than 0. So this means that f bar of t is equal to f bar squared of t over 2. So because of what I have here, this tells me that f bar of t over 2 is f bar of t to the 1/2. But yeah, so now we can say that f bar of, I'll just go there because you know I'm going to generalize this. So I'm going to use like an mt. So m is some positive integer. This is equal to f bar to the m of t. So this implies that f bar of t is f bar to the m of t over m. And this implies that f bar of t over m is f bar of t to the 1 over m. So I can combine both of these, and here's what I can say. Combine the previous two bullets, and I can say that f bar of n over m t is actually f bar of t to the n over m. What I'm trying to claim from this is that f bar of, so I'm looking at rational coefficients. So f bar of qt is f bar of t to the q for all q in the rational numbers. So this is rational numbers. And I might have just said q plus, like the positive rational numbers, which I think is true. And I think it doesn't matter for what I'm trying to show. But I will slow down and write this out carefully in the notes. So here's the one piece of analysis you need. And that is that the rationals are dense in the reals. So the rationals are dense in the reals. So this can mean they're all equivalent, but you can define this dense in terms of limits. But I'm just going to say that it means that between any two rational numbers, you can always find a real number. You can always find a real number. All right, so take any two rational numbers on a number line, there's always something in between them. And so because of this, then I can say, I don't know how much of this I'm going to talk about in the notes, but I can say that this equation actually holds for all positive real numbers x. Okay, so what we've kind of shown so far, I'll have to go think about those negative exponents there, is, and I mean that to be not a q, what am I trying to say? I want that to be a t inside the f and an x at the top. So t, x, that's next, hard to see. So if you plug in, say, t equals 1, you'll get f bar of x equals f bar of 1 to the x. And f bar of 1 is just the tail of the CDF, or the tail probability, evaluated at 1. So this is just a constant, right? This is a c to the x. And c is f bar of 1, but I kind of don't even care. Right. So I can write this as e to the log of c to the x. And using nice properties of logs, I can bring exponents down in front of the log. So this is e to the x log c, and log of c is just a constant. So this is e to the d x, or d being the log of c, just another constant. What? Oh, okay. Okay. I was wondering why I got a positive exponent, because this is telling me, right, this is an expression for the tail probability f bar. So this means that f of x is equal to 1 minus e to the dx, which is looking wonky. It's sort of the exponential CDF, but we do want a negative up there, and we must have a negative up there. And that comes from the fact that this c is between 0, I'll be careful about the endpoints on my write-up, but this c is a tail probability, so it's between 0 and 1. And so when you take the log of c, you actually get a negative, because log, shoots down to minus infinity. So the d is negative. So I'm going to call it negative lambda. It's a constant. And what we're seeing is an exponential CDF. An exponential CDF, which came from only assuming that the random variable was continuous and very nice, and the CDF didn't have any jumps. But assuming lack of memory, we have the exponential. Nice, right? In the discrete case, you could prove that the geometric distribution is the only one with the corresponding lack of memory over there, which we're not going to need. Okay. Any questions while I slowly scroll up? Okay. So yeah, I have more distributional stuff to review, but that's boring. So let me say something about Markov chains. Let's define one. So here's a definition of a continuous time discrete state space Markov process or chain. At the beginning of class, I told you that I kind of stick to a notation that if I'm talking about integer values, I use an x sub n. And then when people talk about continuous time, they absolutely could use an x sub t, where t kind of looks more continuous, although you could define t to be integers. But I like to move to like an x of t when I'm talking about continuous time. So I'm going to let the set x of t indexed over all t greater than or equal to 0 be a continuous time stochastic process. So a collection of random variables, but it's uncountably infinite. Be a continuous time stochastic process. And then I'm going to specify here specifically with a discrete state space that we're going to call S. So with discrete state space S. So this is said to be a Markov process or Markov chain if xt is a Markov process or chain. Well, if the Markov property holds, but we need to be able to define it not, with continuous time. So if for any, like I want some time points. So some S1 greater than 0 and some S2 even bigger, maybe out to a largest Sn, and then maybe an S and maybe a T. And for all states I1 up through IN and an I and a J in the state space, we just need that Markov looking property to hold. So the probability that X of T is J And yeah, we're talking continuous time, but the random variables are still discrete. So it does make sense to talk about this probability. It's not going to be 0. Given all the rest of it, I'm going to write it in time order. I think it's a little cleaner. And xs equals I is just the probability that x of t equals j given x of s equals I. And I do need to say, I'm not sure if I said it last time. I know the conversation came up later and we eventually said it, but this has to hold whenever both of the conditional probabilities are defined. So if you put in something that's not even in the state space, that's not going to hold, your right-hand side probability would be maybe defined and your left-hand side not defined. And that doesn't mean it's not Markov. It just means you don't look there. So when or wherever, where is better? Wherever these conditional probabilities are defined. So probably not surprising, but maybe hard to talk about, previous time steps when there's an uncountably infinite number of them. Oh, and I should say for any n as well, because I did take n plus 2 time points. So this is also for any n greater than or equal to 1. Take any collection of time points of any length. And really, if you have history, the only thing that matters is the most recent piece of history. So, questions? Okay, that was okay. That was too much fun for too long. So we're back to review and the gamma function, the gamma distribution. So keep it as quick as possible. This is another continuous, just like the exponential distribution. So a continuous random variable x has the gamma distribution with parameters. These actually have names, but right now I'm just going to say parameters. Alpha and beta greater than 0. Like there was a lambda in our exponential. If x has the following PDF, probability density function. And some of you are going to say, that's not my gamma. And to you, I'm going to say, it's just like there's 2 exponentials. There's 2 ways to write the gamma. So this is 1 over the gamma function, which I will define, of alpha. So that's a capital gamma of alpha. Beta to the alpha, x to the alpha minus 1, e to the minus beta x. And this holds for x greater than or equal to 0. The equal sign does not matter, and it's 0 otherwise. So this thing is called a gamma function, and I will define it in a moment, but it's just a constant. There's no x's in there. And so is this beta to the alpha. This stuff is just constant. So if you wanted to know the shape of this, really it's the shape of this function of x. And you can see from there that there's kind of 3 shapes you can get depending on whether alpha is greater than 1, equal to 1, or less than 1. So if alpha is greater than 1, then we have an x to a positive power, which is making this increase until the exponential takes over and brings us down. So the shape is kind of like this, and that kind of mound can move around depending on the values of alpha and beta. And I don't want that at all to look symmetric. So let me draw that again. I don't know, something like that. When alpha equals 1, if you go back up to the PDF here, you'll see that this x to the 1 minus 1 becomes x to the 0. So the e to the minus beta x is the only kind of x part left. And that looks like an exponential distribution. And because it's defined on x greater than or equal to 0, if this is going to be a proper PDF, it has to integrate to 1. So if this is gone, because we took alpha to be 1, this is going to force this whole mess of constants to be equal to beta, because we're seeing an exponential PDF with a constant in front of it. We know like that you can have lambda e to the minus lambda x, like 3e to the minus 3x. So 2e to the minus 3x is not going to integrate to 1. However, I still will define this so you can see what the actual constant is. My point is that we have an exponential distribution, and we start at a constant value, which is going to be given by this. And we go down exponentially. And then finally, I'm going to make this small just because I didn't plan well, as usual. If alpha is less than 1, and these parameters do need to be non-negative or we won't have valid PDFs, then we have basically x to a power in a denominator. So this is going to blow up to infinity at 0, and just go to infinity asymptotically as we approach 0. So these are 3 kinds of shapes you can get out of the gamma distribution. And you can play around with your alpha and beta to kind of move this lump around on the x-axis. Okay. I will show you this next time. I mean, I'm not done, but I'm going to do other things. But next time I'm going to show you that the gamma distribution arises as the sum of exponential distributions. And that's why we need it, because we're going to have these processes with exponential inter-arrival times. And so if it was a customer process of people coming in the store and you wanted to know the time until the nth customer comes in, you're going to sum up n exponential times. And that has a gamma distribution. And that's what I have to convince you of next time. I'm sure a lot of you already know that, but some of you don't. So let's talk about quickly the gamma function. Oh, and also notation. So we write, or I should say we will write. This is how I define my gamma PDF. Some people have 1 over betas every place I have a beta. And that would correspond to like the exponential. They've also, parameterized it the other way. So I'm not going to do it 2 ways. I'm always going to do it this way. And I'm going to call this, I'm going to say it has the distribution gamma, alpha, beta to mean that PDF. So when you see 2 arguments in the gamma function, it is the name of a PDF. But if you see 1 argument in the gamma function, it is the gamma function that I'm about to describe. So if you really care what these parameters are called, the alpha is known as a shape parameter. As you can see from these pictures, it kind of determines the shape of the PDF. And the beta, in the way I've parameterized it, is known as an inverse scale parameter. And sort of rescales these things. But it would be known as a scale parameter if you wrote down your gamma distribution the other way. And it's really not important for us. So the gamma function is defined. Gamma of alpha is defined to be the integral from 0 to infinity of x to the alpha minus 1 e to the minus beta x dx. Note that if you go back to the gamma PDF, I don't really want to scroll up right now, and ignore the constants. If you integrate that, I mean, you want the whole PDF to integrate to 1. So if you're integrating 0 to infinity, beta to the alpha, x to the alpha minus 1, e to the minus beta x dx, that's most of the PDF that I wrote above. And I could rewrite this as the integral 0 to infinity of beta to the x to the alpha minus 1, and save another beta, e to the minus beta x, and then I have an extra beta dx. And if I let u be beta times x and make a u substitution, and note that beta is positive, it's actually not going to change the limits of integration. And so beta is positive, and I'll get 0 to infinity u to the alpha minus 1 e to the minus u du. And that is how we define the gamma function. So this is gamma of alpha. And then what I was trying to show you down here is okay if it's there as long as you have another beta in there. So I'm going to scroll back up to the PDF. I just integrated this. What did I do? Yeah, I just integrated the thing I just circled in orange from 0 to infinity and got it to be the definition of gamma of alpha. So this 1 over gamma of alpha is just the constant that makes this PDF integrate to 1. Not that exciting. At this point, I always say, now make up your own PDF, take any positive integrable function, and then even if you can't integrate it, just define the constant to be 1 over the integral and then name it after yourself. Like Mr. Gamma did. No, it's not Mr. Gamma. Okay, I think I'm out of time. So next time I have 3 properties of the gamma function for you, and we'll start continuous time Markov chains. I have one more distribution to review, and that is the Poisson distribution, but I'll wait and just put it in between things so we're not just reviewing all the time. So thank you. I will post review problems tonight, and have an awesome weekend.